Hello, hello, hello. I hope we're all having a wonderful day today. Today we're going to talk about how we can all end up with the same line of best fit, the same regression line. And to do that, we're going to think about this thing called a residual. A residual is the vertical distance between a data point and the graph of our regression equation. So looking at that, that's this distance that's shown in blue for each of these points. Points above our regression line have a positive residual, points below have a negative residual, and if our regression line happens to go through one of our actual data points, we have zero residual. And just to talk a little bit more about this, these red dots are representing our actual data points. If we found the predicted data point, that is, we take our value of x and plug it into our regression equation, we'll get a predicted value for y. The difference between those y values is our residual. When we do a regression, we're hoping to make these residuals as small as possible. That's our overarching goal with these lines of best fit. The best line is going to be the one that has the smallest residuals. That is the line that gets the closest to as many points as possible. So what we're looking at is, we'll be looking at regression lines for this, and our point slope form is here. We use that back in the last section. We were just finding our line of best fit. We're going to use what's called the least squares method to find our equation, and we start by finding the slope. The least squares regression line is the one that has the smallest possible value for the sum of the squares of the residuals. Well, why do we square them? It's similar to standard deviation. If we just added these up, this q would cancel out the p and the r, and we'd be seemingly closer to this line than we actually are. By squaring them all, we're turning all the numbers positive, and we're trying to minimize that sum of the squared residuals. So in this picture, we're trying to make p squared plus q squared plus r squared as close to zero as we can. The only way it can be exactly zero is if the points themselves were collinear. So how do we do that? Well, guys, the formula ain't pretty. It looks like this. The slope of our line is equal to s sub xy divided by s sub x squared, where s sub xy is given by this, the sum of x times y minus the sum of the x times the sum of the y divided by n, and the sum of the x squareds is going to be given by this here. Okay, you're like, whoa, hold the phone. Where'd that come from? Well, if you're interested in where these come from, I posted a link to the development of these formulas, and feel free to go back and take a look at that. It's a little bit involved, and it requires some knowledge of quadratic functions. But we're going to use them. Okay, so here we have a very simple, small example that we're going to find the regression line through these points. We have 3 points that we saw previously, and the last row here are the sums of each column. We have the x's and the y's. We have the x times y's, and those add up to 20, and the x squares, which add up to 14. Our x bar, our average x value, would be 6 divided by 3, or 2, and then 9 divided by 3 is 3. So our mean point is 2, 3. In the previous section, when we were doing line of best fit, we needed this point to start to find our slope from. But now that we have that very beautiful and elegant formula from just a moment ago, we're going to find sxy and sx squared. And if we can divide these two things, we have the slope. So what are they? Well, the formula for sxy says we add up the x times y's, so 20, minus the sum of the x times the sum of the y. Sum of the x's is 6, times the sum of the y's was 9, and then it said divide by n, which is 3. So crunching these numbers, we get 2. Sum of the x's squared, or sx squared. This formula is given by sum of the x squared, so 14. And then subtract the sum of the x's squared. So 6 squared over n, which is 3. And what we get is 2. So our slope is sum of the x, sxy is 2, sx squared is 2. Our slope of our least squares regression line is going to be 1. And now we have all the great little tidbits we need to write our regression equation. Y minus y bar 3 equals 1 times x minus x bar, which was 2. And rearranging this, we get in slope-intercept form, y equals x plus 1. Little bit involved. The calculations aren't too bad once you have this table made, but you might be going, well, you know what, that's great, fine and dandy, Mr. S, but you know what if I have like 20 data points? This seems like it's going to be an awful big pain. And you know what, you're right. It is going to be an awful big pain. And I hope that you never ever do this by hand. We have technology at our disposal, and we're going to use it to do these least squares regressions. Usually when you have data points that you're trying to find a line for, you've got a bunch of them. And to go through this process by hand is very tedious, time-consuming, and not that exciting. So we don't need to do it. You're not going to need to do it on your exams. If you really want to, if you're looking for something fun to do on a Friday night, this will be it if you do it by hand. But we're going to go ahead and use our calculator. So take a moment and take this data table and get it input into your list and spreadsheet. Okay, so you should have it here. There are 12 data points. We've got the distance and the fare. It says use your GDC to sketch a scatter diagram with the line of best fit. Okay, let's see, how do we do that? Well, add a page, data and statistics. We want our distance to be our independent variable. The fare depends on the distance. Our fare is our independent variable, and there's our scatter plot. Now it says to draw, it says we want the line of best fit. Okay, well, let's go to menu, see what we've got. 4 says to analyze. That seems reasonable. We want to analyze this graph. Oh, regression, look at this. And, ooh, show linear regression. Hey, look at that, guys. We now have a least squares regression line. This is the best possible line that we can have. And we have the slope times x plus the y-intercept. Remember to give your answer using 3 significant figures. So 0.117 x plus 83.3. So this is B. Now, let me show you another way that you can get there. You don't have to make the graph for it. If I come back to my table and go to menu, let's go to statistics, our good friend statistics. Now we want to do some stat calculations, and oh look, choice 3 is a linear regression. Just as a point of interest, both of these do the same thing, just notice there are different names for the slope and the y-intercept. This number 3, slope is called M, y-intercept is called B. This one, slope is called B and y-intercept is called A. Doesn't matter which one you use, you might be used to seeing mx plus b though. So x list was distance, y list is the fare. Save regression equation to F1. Frequency list is 1, we're leaving that alone, we hit OK, and boom, here it is. Mx plus b, m is 0.117, B is 83.03, same thing we got. And we're going to talk about this R value later, but here are the residuals. That's what the residual for each point is as we compare it to the predicted line. So, the last thing to show you here would be control. I'm going to add a graph. And notice it started on F2. If I press the up arrow, ooh, there we go. Look at that. Cool. So I'm going to change my y-axis. Let's go up to 100 maybe. And I still don't see it. Ooh, that's a little unnerving, right? So I go up here. It's because this box isn't checked. There it is. We want to be able to see this graph. There it is. Look at that. And the question is, use your equation to estimate the cost of a 1,000 kilometer flight. So what we're really doing here is plugging in 1,000. And we crunch the numbers, and what we end up with is $200. And you might be saying, wait a minute, that's more than 3 significant digits. And it is, because we're talking about money, so it's appropriate to give our answer using dollars and cents. So there we go. Your calculator is 100% going to be your best friend for this section. Have a wonderful, wonderful rest of your day.